Sikhora holds Master of Electrical Engineering and a Master corresponding MP of Business Administration, both from Action Technical University, Germany. He is a DAD alumnus from 1991 in St. Petersburg Polytechnical Institute. He has done a PhD in Electrical Engineering at the Fraunhofer Institute of Microelectronic Circuits and System, Duisburg, with a thesis on SOI technologies. After various positions in the telecommunication and semiconductor industry, he became a professor at the Baden-Württemberg Cooperative State University laureate in 1999. In 2011, he joined Offenburg University of Applied Sciences, where he now leads the Institute of Reliable Embedded Systems and Communication Electronics. Since 2016, he is also a deputy member of the board of Sikhora Association of Applied Research, a government-funded research institute in the state of Baden-Württemberg. There he now leads two engineering divisions, embedded solutions and software solutions. Since 2019, he is also affiliated to technical faculty of Freiburg University. His major interest is the field of efficient, energy-aware, autonomous, and value-added algorithms and protocols for wired and wireless embedded communication, with a strong focus on end-to-end security concepts and implementations for the industrial Internet of Things. Dr. Sikhora is founder, shareholder, or board member of several startups, mainly Stackforce GmbH, an independent and successful spin-off engineering company around wireless and low-power wide area network-based IoT connectivity solutions for smart metering and smart city applications. Dr. Sikhora is author, co-author, editor, and co-editor of several textbooks and more than 200 peer-reviewed papers in the field of embedded design and wireless and wired networking. Among his many other duties, he serves as chairman of the annual Embedded World Conference, the world's largest event on the topic. So, such a world-renowned person is here for us to deliver to handle this session. I welcome on behalf of all the participants to this FTP, sir. Welcome, sir. Session is handed over to you.
Okay, thank you very much, Marina. It's a pleasure to be with you, even remotely, for the second time now, to report on IoT activities for agronomics applications. Before we start, I see there's a hands up from Senthil Kumar. Is this by purpose?
Oh, pardon?
There's a hands up from Senthil Kumar.
Senthil Kumar. Okay, we will address it.
Yeah, okay. But then let me share my screen and start the presentation. I hope you now see my screen.
Yes, sir. We can
fine.
see.
Okay, I leave my camera open so that you also see my face. What I prepared for today, for the next 90 minutes or maybe 81 minutes now, is the following structure. First, I would like to give you a very short introduction of where I come from and what my background is, then give you a very short introduction about into the IoT as such, beyond agronomics, and then go into the much more technical chapters which talk about IoT architectures, the service models, and also the IoT platforms. After that, I want to show you 3 use cases from our projects, which I believe are pretty much representing what is going on in the field of agronomic IoT. The world is very complex, so there might be very many and thousands of use cases, but I just thought it might be interesting to see for you where exactly a research university like we are making our sweet spot. Of course, I will finalize with a summary and outlook. Yeah, disclaimer, we discussed this earlier, Mary, Rena, that I use some photos from the internet where I don't have the copyright. I always try to give the references, but this slide deck is not or should not be published openly in the internet. Okay,
Yes,
where do I come from? If you take a look into European map, you will see Germany in pretty much the middle of Western Europe. Our location in Offenburg is in the southwestern part of Germany, a little bit like Kerala is in the southwestern part of of India. However, we don't have the sea around us, but our neighboring countries, especially France and Switzerland. And to be more precise, the region is what we call the Black Forest, which is a very nice rural area. I don't have pictures now from the cities, but from the region. So in summertime, it's very, very green, very nice. And in wintertime, there's a lot of snow. So it's also a little bit like Kerala. It's also kind of paradise holiday region. To be even more precise, you might know the Black Forest cake. This is a photo that I took a couple of years ago when I was at Mysore for some physical training at JSC University. And when I walked into the hotel, in the lobby, I found the Black Forest cake, which was offered there. So originally, this comes from our region. This is Black Forest. So coming to the technologies and the background at the university, I do have a pretty large research team of PhD students and research engineers, where we are working pretty much in the field of stack development and protocol stack implementation for the IoT, which then also implies the software engineering, because most of the stacks are, of course, being programmed in embedded C typically. Sometimes we also do hardware software co-design. This is especially important when it comes to embedded security, where we also need crypto accelerators. When it comes to security, which is for me one of the most important issues, then also we don't sit only on the good side, but also take the bad side and do the attacks and the data analytics, sometimes using machine learning and artificial intelligence, but sometimes also just using legacy old-fashioned technologies. And in doing this, of course, test and verification is also a very important thing to make complex systems work reliably. What might be quite special for our situation is that there's a lot of collaboration with industrial partners. And if you see the list of logos, maybe you know very few of them. There might be big companies like Bosch or Vaillant or Deutsche Telekom, which are potentially known also outside of the region or continental. But most of the companies that we collaborate with are mid-sized companies which need technology support and research support. And this makes our excuse me, our activities pretty much applied. So we stand on both legs, both on the research leg and the applied research or development leg. In having said this, we are also partnering with many associations, most notably with the Profibus Profinet International, where we are active in the standardization CAN in automation for the CAN bus is also very important. And for us also the OMS group for open metering system is also one of the major platforms. In Germany, we have collaborations with many other universities, but what I want to mention here is that there's also a lot of collaboration from our institute, not from the university, which comes on top, but lots of bilateral collaboration with universities and research partners all over the world. And this is very much appreciated and gives us a lot of influx also for new ideas and new stuff. In parallel, Maririna mentioned this. I'm delegated to a research institute, which is under the umbrella of our Ministry of Economics, our state ministry. And with the Hans Schickard, we have 4 centers where I'm deputy head of the Institute of Micro and Information Technology in the very middle of the Black Forest, where we do a lot of research from sensor to the cloud. So what we do have is microtechnology and MEMS for sensors and actuators, microelectronic and mechanical systems. Then we also do have smart sensing with the electronics and ASIC design. And then finally, and this is my major baby, the software solution, which adds the cyber part to the cyber physical systems. And what is fascinating for me is that we can do the complete value chain from sensor to the cloud under one roof, having all the colleagues with us, and this is a very nice positioning. In addition, as Irina also mentioned, I'm looking after a few spin-offs, most notably about the StackForce company, which is again doing stack development, but on a professional commercial level, mostly for the smart metering and for the low power wide area fields like LoRa, WAN, Sigfox, MIOT, and so on. Okay, but let's go into the IoT world. If we look into the history, we see that in the very early days, we had sensors which translated physical signals into electrical signals. So analog physical input, electrical analog output. In the second step, this was added with a interface circuit to generate standardized analog electrical signals, like the 4 to 20 milliamps current loop that we still have, like the hard bus, for example. However, having analog signaling is, of course, tedious, error prone, and also expensive to implement. And therefore, people back in the 90s very rapidly adopted microcontroller technologies, embedded technologies to generate digital signals, which is not only the ADC, the analog digital conversion, but also potentially some signal pre-processing to make a sensor a smart sensor. And then in the late 90s and early 2000s, these smart sensors increasingly were connected to local networks. They got their network interface. Field bus technology came up, and this then added to the idea of having a sensor node in a complete network. But and this is maybe something which is then leading to the Internet of Things. All these sensor nodes have been connected to the sensor network, and then also to uplink systems, backend systems, to cloud-based systems. And then there we are in the Internet of Things. If we are talking about the wording, then for me, many of these words are pretty much overlapping. So I already mentioned the Internet of Things. I'll come back to this in a second again. Sometimes if we have single sensors being connected with the cellular communication, then we also talk about machine-to-machine communication, which I find is a very nice description of not having humans in the loop, but having autonomous, automatic communication between automated machines. Also, as I mentioned with regard to the Hans Schickard, I also like the notion of cyber physical systems, where we have the cyberspace connectivity of physical systems, sensors, and actuators. And of course, from especially the German point of view, we also like the wording of Industry 4.0, the fourth industrial revolution, which makes or which provides the connectivity and the full visibility and also the full intelligence of distributed systems. If we look into the history from another point of view, we see that there have been several phases. Phase one, I like to call smart things without connectivity. That means having the smart sensing with local intelligence, but not really a networked interaction. And this is maybe also important to understand that these systems still do exist. If you look into your dishwasher, your washing machine, all your home appliances, but also when you look into local sensing nodes for the agronomic fields like temperature sensing, gas sensing, then all these devices belong to this first phase. If you connect these smart devices in local networks, like in home automation, but potentially also like in industry or in a farm, then we have a local distribution of sensors and actuators. And this is something that I like to call the net of things. That means we have devices being locally interconnected. On the other side, pretty much parallel to the second phase, third direction developed, where single devices were connected to back-end systems. This was mostly started from the energy field utilities, which read out smart meters and to send out automatic invoices and also remote areas like for agronomic applications were involved into that. This is something that I like to call single things in the internet. So not complete networks being interconnected, but single sensors, single actuators. And it's only the last phase, which started maybe 20 years ago already. So the trend is not very new as such, but the speed has pretty much accelerated even over the last years. And this is what I call Internet of Things, which you might know is a mountain region in the middle of Europe, in Switzerland, Austria, south of Germany, France. So pretty much along the middle of Europe. And in this project, which has been funded by the European Union, a number of different partners joined, which is apart from our organization, Hans Schickard, which is also consisting of the associations of milk producers or of animal producers. So those associations where farmers are members of. And what we see is that we wanted to monitor the well-being of cattle, of cows for milk production, with each cow having a sensor, in this case, in the first step, an outside sensor, but potentially, potentially also a in body sensor, which then transmits the information to a local gateway in the boxes, then potentially also to a second level gateway in the barns, and then go to over the internet to the backend service. And also here we see that there are two kinds of service coming back to what I already explained earlier. So there's a data path for collecting the net data of the well-being of the cattle. And there's an admin server, which does all the commissioning, management, security, administration of the complete system. Let me show you some pictures. So cattle is equipped with sensors, which are two kinds of sensors. One is a microphone, and because the microphone is mounted very close to the cow's body, you can also listen to, how the cow is chewing, is ruminating, whatsoever. And there's a second sensor, an inertial measurement unit, accelerometer, which then can track the motions of the cow. These sensors are mounted to the neck of the cow. In this case of the SESAM project, about 2,000 of these sensors have been distributed to different farms, where then in the farms, the gateway collects this information via Bluetooth and forwards it to a central gateway via Wi-Fi. The central gateway is then a larger gateway, which then has also the backend connectivity to the backend system, both to the admin server, but also to the data server. And again, we see here this hierarchical approach of sensor, first level gateway, second level gateway, and so on. Yeah. And we also see very nicely this split between data path on one side and management path on the other side. And I believe that we also easily understand that the cost of such a system is pretty critical. The more expensive the system will be, the less farmers would invest into the money, would invest into such a system, because they don't benefit enough. The increase of efficiency would not be big enough to justify these investments. So we also analyzed the data and especially classified 5 different activities of the cattle, which is walking, which is ruminating, eating, laying, standing. And then we take the accelerometer values as input, calculate the feature sets with a pretty high sampling rate, and then predict the class with the highest probability. And what we see is that the accuracy of such a machine learning based analysis is pretty high. Of course, it could be even higher if we add additional sensors, if there also would be camera-based systems, if the quality of the inertial measurement units would be higher. But again, here we believe that the trade-off between cost on one side and accuracy on the other side is critical for the final success. Okay, and then let's mention also a third use case, which goes around safe food processing. 2 projects can be mentioned here. One is called BIS, abbreviation for blockchain in the control cabinet, which has been a research project with also a couple of companies and partners being funded from our state. And again, it goes around food production, in this case of a so-called black forest ham, which is generated or produced from pork, and which of course needs high quality meat on one side, which also needs special processing in the smokery, and where we want to track all relevant information. So this again is about the monitoring, and where blockchain comes into the game is where we want to have immutable tracking of monitored information. So we have a complete value chain for this information. We had a second use case, which was not from food production, but from machines. But basically, all the information and the stakeholders were identical. Based on this, we generated a second project together with a research partner in Ghana in Africa, where we also go for safe food production, connecting all the different elements from the sometimes big factories into immutable ledger elements to allow a complete monitoring of the process in distributed systems. The beauty of this blockchain, of this distributed ledger approach, is that we believe that it can be completely decentralized, and there is no need for this, well, John Deere tractor land machine approach where everything is integrated from one single company, but where trust can also be established between the distributed and equal partners. So what we see here is, as I mentioned, the beauty of distributed ledgers. We have distributed storage, decentralized architecture, the immutability, also the possibility of having smart contracts, automated activities, and resource sharing. However, we also fight with several challenges. The reliability of the sensors itself. If you deliver rubbish into this database, then you also would get rubbish out. Ledgers are still very costly. Also, in many cases, they are managed centrally from an authentication point of view, which come to a very short summary. Oh, there's a problem with this slide, but let me give it in words. I believe that IoT is rapidly advancing. It's very successful with verticals, like with agricultural applications, and we see very many interesting applications also in this field, which are rapidly advancing, but which still come also with lots of interesting challenges for cost reduction, reliable operation, scalability, and overall integration. So let me thank you for your kind invitation and for your interest in listening to this presentation. I'm 2 minutes over time, sorry for that, but then we have another 28 minutes for an interesting discussion and potentially also some nice joint ideas. Thank you.
Okay, sir.
Okay, Marina, would you like to moderate the Q&A session, or shall I ask for questions?
Participants, you may ask questions. You can unmute yourself and ask question directly. And chat box also, we have received some questions. So those who want to interact directly, please. Sir, it was a very good presentation explaining the things very clearly and in a simple way. So I think most of the participants, they have enjoyed the session much and followed the contents also. So, I want to ask one doubt regarding that cognitive nature of the IoT networks. So when we move to the application of the self-driving cars and all, this edge computing is more relevant. It's more getting important than that of the cloud processing, which may take more time. So in that scenario, this cognitive framework or the intelligent Internet of Things, how it can play.
Yeah, I mean, as I said, I don't believe that we should play, or we should make a decision if this was edge computing or if this was cloud computing. I mean, this is also kind of commercial war of the different sides. The Microsofts and the Amazons of the world like to promote their cloud-based computing. Other vendors, of course, promote their edge computing approach. In the end, I believe that the combination of both is maybe the most realistic way, because shuffling all data into the cloud normally is not efficient. It's costly. It's millions of bytes or trillions of bytes, and very costly, because you have to pay for the data transfer and the data processing. On the other side, if you go for edge computing only, you run into lots of practical problems. Just start with backup of your information. If one of the edge nodes fails, goes out of operation, then this local information is lost. If you talk about federated learning, for example, that means consolidating information, then this certainly is also a task that a single edge node cannot execute. If you also talk about, well, backward learning, adaptive learning, then this is again something which only a cloud-based system can execute. So as I said, I believe that the combination of both good sides is the optimum. And where the actual optimum for a specific system is, this pretty much depends. But this, again, is the interesting part of applied research, where we optimize and adapt the systems to the specific applications.
Okay, well, sir. There is one query in chat box. How much it costs to form this cattle monitoring by using IoT? From Arun Kumar.
Question. This is an easy question with no easy answer, because again, it depends, I believe, on the industrialization. Obviously, if we calculate the complete project cost, which is around 2 million euros or $2 million for 2,000 sensors, then it is about 1,000 euros per sensor, which is extremely costly. On the other side, if you have a scaling effect going into larger numbers, then the perspective of having a sensor for a hardware cost of maybe 20 euros, which I believe is pretty reasonable, at least for bigger animals like a cow. When it comes to smaller animals like sheep or pig or even chickens, then again, this still would be too costly. Yeah. And again, here, let me repeat that the success of such systems is not decided by technology only, but by economics. And this needs to be clear. And cost optimization is key here. What we also should not forget, at least for our environment, where human labor, especially highly skilled labor, is expensive, that also the operations of such a network is a significant aspect. So if we look into the total cost of ownership, the investment into the hardware and the mounting of the gateways and the setup of the service and the purchase process for the sensors is only one side. But we also see that the operations and the HR resources, the human resources for keeping things up and running, and for also triggering events in case of problems, that this is a significant part. Depending on the numbers, it might be half, it might be 25%. It depends on the numbers, how many sensors you are looking after. But it's nevertheless, this operation cost is a significant part to the total cost of ownership.
Okay, I think it answered. It is sufficient for that question. Then another query is Jayalakshmi M asks, sir, can you suggest some research problem in the agriculture domain using IoT and blockchain? Some research problems in the agriculture domain using IoT and blockchain.
Yeah, I mean, I mentioned this project with KNUST in Kumasi in Ghana, and here we currently have 4 PhD projects running. One is about the authentication of the different stakeholders, especially low-end stakeholders, which are not highly industrialized, but which are small farmers in Ghana, how to connect them into a purely distributed system. We also look into the scalability of such systems in terms of which information really needs to be stored in the blockchain, which information can be stored also in auxiliary databases and only hash functions. Some meta information needs to be stored in this blockchain. So this is a second challenge that we are looking after. A third one certainly is also the scalability of such a system, because blockchain systems don't scale as such. And a fourth one again goes to the authentication and the integration of trust management systems into such a distributed system, which I believe are specific aspects for the blockchain related research questions. When it comes to the application, analyzing the data, understanding, well, as I explained earlier in this phase model, understanding why things are happening and making predictions what will happen. These application-oriented questions, I believe they are really endless. But also, to be honest, because I'm a communications and IT engineer, I cannot comment so much on them because I'm not on the application side as such.
Okay, thank you, sir. If any other queries, the participants can unmute yourself and ask. Sir, can you differentiate between the federated learning type of algorithms apart from other machine learning algorithms?
Yeah, I mean, what we do in machine learning is collecting data and optimizing neural networks in such a way that the total error is minimized. In normal one-step architectures, you do this in a single step way in terms of collecting all the data and feeding this into one neural network and doing the optimization. If it comes to federated learning, then we do it in a two-step or even multi-step approach. Well, typical systems up to now are typically two-stage, but you could theoretically extend this, where you do this optimization locally, either with a subset of sensors or only a single sensor, and do this optimization locally, and then replay this learned information to a second network and do the optimization there again, which comes with two major advantages. One is that the amount of data which is forwarded to the cloud, to the backend system, again, is limited. So you reduce the capacity of the transport channel. You also reduce the cost of the backend system because there's less data to be processed. And very importantly, you also increase the privacy of your system because you don't share your raw data, but you only share your pre-trained model. And this is a very crucial point for many applications. At least here on our side, people are very reluctant to share their production data, because from this data you can also make additional or you could generate additional information about the money situation, the financial situation of this company or of this farmer, about any problems from the outside. So people are very reluctant to openly share their raw data. And therefore, this second aspect of privacy is also one of the major advantages of the federated learning. However, nothing comes for free. You need additional computing resources, learning resources, also at the edge or at a gateway, which needs additional computational resources. But I can also mention that at least here at Hans Schickard, we have a very nice activity about the embedded machine learning or embedded AI to optimize algorithms so that they that not only the inferencing but also the learning algorithms need only reduced computing resources. There are lots of ideas around that, and therefore I believe that this combination of embedded AI on one side and federated multi-step distributed learning will be also very promising for many applications, not only for agronomics, but in general.
Okay, sir. So we hope that in future, very cheaper embedded AI systems will come into existence, and we can have better design for systems.
Yeah, let me comment this. Maybe don't wait for them, but work for them.
Okay. Any other queries? Please ask. I think no other queries from the participant. So once again, we are very grateful to you, sir, joining with us for this second series of this faculty development program on Internet of Things development. So we think that most of the participants got benefited. Here the participants are from different backgrounds, say some from agriculture side, some from computer science, because it is the combination of both. So I think this is also a good avenue that they can share the expertise and work for a common goal. So many of the participants that they got benefited out of your talk, and they got many ideas, and understood the things. So on behalf of all the participants and from my institute side, we extend a heartfelt gratitude towards you, sir. Thank you very much, sir, for spending this much time for us and accepting our invitation. So we hope in future also we we can have your such type of expertise, sharing of expertise with us, sir. Thank you very much.
Oh, thanks for your invitation and for your perfect organization. Thank you very much, Marina. Thanks to all.
Thank you, sir.
All the best. Yeah. Bye.
Thank you, sir. Bye. Okay. Next session, we will join 11:30 sharp. So please, all the participants, you can take as a break of 10 minutes and join back by 11:30. That next session by again IoT framework development of Mr. Shrikant M. Dr. Shrikant M. Okay. See you. No. Hello, Shrikant. Hello, Dr. Shrikant. Can you hear me? Hello, Shrikant. Hello, Dr. Shrikant. Can you hear me? Hello, am I audible? Shrikant, can you hear me?